Okay, thank you very much, everybody, for coming in. We will do a quick recap of the questions that appeared in the midterm exam, and then we will continue from there. Let's see how far we can get today. Okay, so the first set of questions, which were simple one line or couple of sentences, maybe a figure kind of questions. So the first one, distinguish between the terms specific yield and specific storage. Most people got this right. The distinction is fairly obvious. Uh, Specific yield is a term that is used in the context of unconfined aquifers, and it refers to the volume of water that is released by the aquifer per unit area of the aquifer per unit decline in head. So that's the definition of specific yield. Specific storage, on the other hand, is mostly used in the context of confined aquifers, and it is the volume of water released. Now, there are two ways of saying this. It's the volume of water released by the aquifer per unit volume of the aquifer per unit decline in head. That is one acceptable definition. The other definition would be it is the volume of water released by the aquifer per unit area of the aquifer per unit decline of head per unit thickness. So it would be per unit area per unit thickness. So that can also be called per unit volume. It's not a problem. So either definition, if any of you said it or wrote it, that's an acceptable definition for the term specific storage. Now, one point that probably not even nobody, almost everybody answered this question right. Okay, so it was fine. But even those who answered it correctly did not mention this. There's another difference between these terms, the term specific yield and specific storage, is that apart from the fact that one is for unconfined and the other is for confined, is that the magnitude of these terms. Specific yield, the magnitude is around 0.1, 0.15, 0.2 of that order, whereas specific storage is really low. It can be 10 power minus 4, 10 power minus 5, and so on. Okay, so that is another distinction between these two terms, right? Specific yield is about 100 times or maybe even 1,000 times larger in magnitude than specific storage. Okay, all right, so that's the first part of the question. Second one, the porosity of a uniformly graded soil sample is independent of the grain size. Is this statement true? Explain briefly. Now, this statement is true because now, when we talk of soil samples, we are idealizing it as perfect spheres. Now, obviously, no soil sample is actually a sphere or will actually consist of perfect spheres. But in the idealization, if the soil sample is a perfect sphere and if all the spheres are of the same size, then irrespective of the grain size, the porosity of that sample will be identical. If I have two soils which are both uniformly graded, means all the grains are of the same size, right? And if they are all spheres, then a uniformly graded soil sample, irrespective of the size of the diameter of the grain, will always have the same porosity. This is something that we did in class probably in the early part of the semester, and if you accompany this with a figure indicating different spheres of different sizes having the same porosity, you can again, as I said, most people got this question correctly, so there was no problem. But some people probably either probably missed the first portion of the course or had some other understanding. Anyway, okay, so that was the second one. Third one now. Okay, if there are questions, please unmute yourself and speak up, especially those who are not attending the class in the room. If there are people in the room who have a question, you just have to get hold of the mic. So, Raish, the microphone is available that can be taken around the class.
Yeah, no questions, sir.
No. Is there a microphone available that can be taken around?
Yeah, microphone is available, sir.
Excellent, thank you. So if there are questions at any point, please just unmute yourself and you can ask your question, whoever is in the classroom, whether it is one person or 5 people or 10 people. Okay, all right. So the third question, why does Darcy velocity not represent the actual pore water velocity in porous media? For the Darcy velocity, by definition, is the flux per unit area of the aquifer, right? Or the porous medium through which the flow is happening. So the unit area of that soil sample or the aquifer includes not just the pore areas, it includes the entire area occupied by the soil particles as well. And so the flux, the actual velocity is determined by the pores, the porosity. It's not determined by the overall area. So the Darcy velocity, although it's called velocity, it does not represent the pore water velocity in the soil through which the flow is happening. Okay, so this one also, I think pretty much everybody got it right. So uh, I'm, I don't think there's any major gap in the understanding for the majority of the class. Okay. So now the fourth part of it. Why is a falling head test not preferred for estimating the K of coarse grained soils? Again, this was something that most people got right. So the falling head test relies on the principle that we measure the time taken for the water level in a tube which is connected to the soil sample, the rate at which the water level falls in that particular tube. We measure the time taken to fall from a certain height to a certain height. And using that, we estimate the hydraulic conductivity of the soil sample under consideration. Now, what happens in the case of a coarse grained soil is that the time taken for that water level to drop from a certain height to another height is so short, or it can be really small, which makes the measurement of the time taken very uncertain. So, for instance, if it takes 2 seconds to drop from a height of 10 centimeters to 5 centimeters or whatever it is on the apparatus, there is an associated reaction time. When you're measuring time, you have a stopwatch and so on. So when the time being measured itself is so short, if you add on the reaction time, which could potentially either subtract or add to the total time, it plays a big role in it adds a higher level of uncertainty in the time estimate, and therefore it is not preferred for estimating the hydraulic conductivity of coarse grained soils. So if I have a coarse grained soil, we typically we do the constant head permeability test, where the head doesn't vary as a function of time, but we collect a volume, the volume of water collected, and we measure the time taken to collect a known volume of water, and we use that to estimate the hydraulic conductivity of coarse grained soils. So the falling head test is preferred generally for fine grained soils, not for coarse grained soils. Okay. All right. Then briefly explain the method of estimating drawdown in an observation well that is located near a hydraulic barrier. Now here, of course, most people got this right again. Maybe, okay, 40-50% of the class got it right. What I would say is, if in answering this question, right, all you do is draw a figure showing the pumping well, the barrier, right, and the imaginary well. And if you indicate that one well is going to pump, the other well is, in this case, it is going to pump, it is not going to inject, right? If you just show a pictorially, if you represent it, as they say, a picture is worth 1,000 words. So instead of writing a big story about when there is a hydraulic barrier, an imaginary well will be placed at the same distance away, which is not wrong. I'm not saying it's wrong, but a simple figure like this, let's say, I'll try to, oops, sorry. Okay. Seems like I've forgotten how to do the online lectures. So, okay. So this is my land surface. This is my pumping well. And I have this hydraulic barrier somewhere here. Okay. And let's say I have an observation well at some distance over here. Okay. And this well is pumping water out. Now all I do is extend this imaginary domain. This is at a distance. I'm so sorry. I don't know why it's misbehaving so much. So let us say the well is at a distance of r meters from this hydraulic barrier. Then I place this imaginary well at the same distance r from this barrier. And now remember, this barrier, the, what it is achieving is that it is preventing water from entering the aquifer from that boundary. Okay, which means Thai solution is assuming that some water is going to be coming in from that boundary, right? Thai solution assumes that the aquifer is infinite, but in this case, the aquifer is not. So there is actually a loss of water to the, if the aquifer had been infinite, some water would have come from that portion of the aquifer. So what I do to mimic the fact that this particular situation is not in line with the assumption that we made in the Thai solution, we say that I will add an imaginary aquifer on the other side as well, which doesn't really exist. And instead of, and I'll also place a pumping well at the same distance r from the boundary as the actual pumping well is. And to mimic the fact that this aquifer is not providing water, I will additionally pump out water. Now, some people um, said that I will inject water into this aquifer. Now, that would be a correct answer if this boundary was not a hydraulic barrier but was a river. If there was a stream here which was providing water to the aquifer, then you will pump water into the aquifer. But in this case, I have a barrier which is preventing water from coming in. So therefore, the imaginary well will also pump water out. It won't pump water in. So all you need to do really is to draw this figure, and then you're done. You can probably add one sentence which says the drawdown at the observation well is equal to drawdown due to the real well plus drawdown due to the imaginary well, and you're done. That's it. That's all that you really need to do. So what I would suggest is, wherever possible, try to have uh, try to make simple um, these kinds of pictorial representations which convey everything that you want to convey. There is nothing additional that needs to be conveyed. You don't have to write 1,000 words. This picture will convey everything that needs to be conveyed. Okay, I'm not writing imaginary well on that side, right? So you just have to write imaginary well, pumping well, observation well, and then you're done, right? Any questions? Okay. Now the last part of the first question. A two-layered aquifer comprises of a layer with K prime, oh, sorry, not K prime, K equal to 0.1 meters per day and a thickness of 15 meters, and another layer with K equal to 10 meters per day and a thickness of 25 meters. Compute the effective hydraulic conductivity of this system if the flow is parallel to the layering. Okay, parallel to the layering means I have one layer and I have another layer. The hydraulic conductivity and the thickness of each layer is given. This question, again, most people got it right. Of course, some people uh, probably misunderstood this parallel to the layering, what it means. Parallel to the layering means the flow is going in this direction. This is parallel. If the flow is going across this way, then that would be perpendicular to the layering. Okay. So the effective K is simply sigma Ki Bi divided by Bi. Right? K effective is sigma Ki Pi. Really don't know what to do with this. Well, anyway, it is what it is. No point in complaining about this. Okay, so the effective K will simply be sigma Ki Bi divided by sigma Bi. So in this case, it comes to something like 6.5 meters per day or something like that. Okay, I don't remember the exact number. So it will be 1.5 plus 250 divided by 40. So around 250 divided by 40, basically. Right? Okay. If there are no specific questions on any of these 6 subdivisions, we will move on now. Okay. Okay. The second one, identify the system for which the following governing equation is applicable. Also indicate what each term in the equation represents. Okay. So now this equation, what I was looking for, a lot. Okay. The first part, and in this entire question, a lot of people got it right. A lot of people wrote this equation is applicable for an unconfined aquifer. I didn't penalize anybody if they wrote that. But what I was expecting was it is applicable for an unconfined aquifer that is heterogeneous, anisotropic, has sources and sinks, and is in a transient state. So that was what I was expecting. But in any case, those who wrote just an unconfined, two-dimensional unconfined aquifer, I did not penalize anybody in that, if that was the answer. Okay, so the first part of the answer is what is that it's an unconfined aquifer. The second part looks like a lot of people either forgot or missed reading. Also indicate what each term in the equation represents. Now, when I said term, some people misunderstood that for what does K mean, what does H mean, what does N mean, what does Sy mean, and so on. Okay. What I meant was the first term is dou by dou x of kx into h into dou h by dou x. That is the term 1. And then second term is dou by dou y ky h dou h by dou y. That is the second term. And then n, and then sy dou h by dou t. Right? Some people understood it correctly also. So, I mean, nothing to say about it. But most people, probably the majority understood it as what is kx, what is h, what is x, and so on. And they explained that, which is also okay. I didn't penalize anybody for that as well. So the first term, what I meant, the first term is the net flux in the x direction. The second term is the net flux in the y direction. N is the external flux that's either coming in or going out of the coming into the aquifer or going out of the aquifer. And then the term on the right hand side is the net change in storage in that in that aquifer. So that is what I was expecting in the second part of that first sentence, the second sentence basically. Okay. And then simplify the equation for the special case of a heterogeneous isotropic aquifer. Okay. Now, heterogeneous means that kx or ky is not constant in space. Heterogeneous means things can change at different points in space. Isotropic or anisotropic, what they mean is isotropic means things don't change with direction, right? At a particular point, if I have kx and ky, they will be equal. That's what isotropic means, right? Heterogeneous isotropic means kx and ky are equal, but they can be different at different points in x and y. Okay, so that's what the first equation will be. So the first equation, the first part, I would rewrite the same equation, but instead of writing kx and ky, I'll just say k. So it will be dou by dou x, k h dou h by dou x plus dou by dou y, k h dou h by dou y plus n equal to sy dou h by dou t, right? So all I have to do is in this equation, in the equation that's given, I simply remove this x and this y and replace it with just k. Okay, so that will take care of the first part of the question. Now the second part, a homogeneous isotropic aquifer. Now as soon as I say homogeneous, I'm indicating that both x and y, both hydraulic conductivity in x and y directions are not dependent on x and y, which means k is constant for different values of x, or kx is constant for different values of x, and ky is constant for different values of y. So that's what homogeneous means. Now, in addition to that, I'm also saying that it's an isotropic aquifer, which means that kx and ky are the same. So all you do is, you just, for the second part of the question, you will get rid of the k inside this parenthesis and bring it out. So it will be k times dou by dou x, h dou h by dou x, plus dou by dou y, h dou h by dou y. The k is something that's constant for both these terms because it is homogeneous and isotropic. Okay. Second question, the third question is homogeneous and anisotropic, which means kx and ky are not equal, but kx itself does not depend on x and ky itself does not depend on y direction. So then the kx term will come out of the parenthesis of the first term, and so you will write kx times dou by dou x of whatever is left in the parenthesis plus ky times the next dou by dou y of the parenthesis, the term inside the parenthesis. Okay, so that's what the third part does. And then the fourth, the final one, is the steady state flow. I will simply make the right hand side go to 0, and that takes care of the steady state condition. Okay. And then the final part of this question was, mention any one method of linearizing this equation. Now, in class, we discussed two ways of linearizing. One was to say that this h dou h by dou x can be written as dou h square by dou x, half dou h square by dou x, and so on. And similarly for dou h dou h by dou y, you write it as half dou h square by dou y. And then you do some simplifications. That is one way of linearizing this equation. But what you get in that case, the right hand side, you still have to be careful, because the equation is linear only if all the variables, both the left hand side and the right hand side, are the same. So if I have dou h square by dou x and dou h square by dou y on the left hand side, I also need to have a dou h square by dou t on the right hand side. To do that, you have to do some simplifications. So if you just go back to the notes to our previous lecture, you will find that first way of linearizing it. The second way of linearizing it is to say kx times h and ky times h. These are some kind of constants, and you can call it the transmissivity of the average transmissivity of the aquifer in the x and y direction is more or less the same, and therefore you can replace this kx into h in the first term. You can just replace it with a t average, and similarly ky times h, you replace it with a t average, and then you're left with an equation that seems identical to the equation for the confined aquifer, because you have now replaced kx times h with the average transmissivity of the unconfined aquifer. Okay, so again, this is one of those questions where quite a number of people were able to identify most aspects of this particular problem, but there were some issues with heterogeneous isotropic, homogeneous isotropic, and I think particularly heterogeneous isotropic was something that a lot of people had a little bit of issue with it. The rest of it was, I think it was okay. All right, any questions?
No, sir.
Okay, no questions. Anybody who's attending, who's not in the classroom, are there any questions? You can please unmute yourself and speak up. Okay. So now let's go to the third question. This one I already explained in class yesterday, but just for the sake of completeness, I'll probably mention it again. So what is given in the problem is there's a pumping well which is pumping at a certain rate for 100 days, and then it is turned off for the next 100 days. And then I'm asking you to write an expression for computing the drawdown at an observation well at a certain distance at any time t where, and I give two conditions, t less than or equal to 100 days, the first 100 days, and t greater than 100 days. So how does the expression for drawdown change as a function of time? Now, the answer to the first part of the question is already in front of you. It's already given there uh, in the Cooper-Jacob approximation. S equal to Q by 4 pi t, well function U. That's it. That's the answer to the first question. So that's nothing really difficult about it. You just write that down. To the second part, this is something that probably a majority of the students did not get, is that you need to remember that Theis solution assumes that the well is pumping for an infinite duration. Now, in this case, it is actually stopping pumping after 100 days. So, in order to mimic that, what we do is after the 100th day, we turn on another well at the same location, at the same point, which instead of pumping water out, pumps water in at the same rate, 100 cubic meters per day. Now, the combined effect of that is that I pump out 100 cubic meters per day and I pump in 100 cubic meters per day, and these two cancel each other out. And so, therefore, the net pumping from time 100 t greater than 100 days onwards is 0. So, there is no net pumping after 100 days. Okay. So, that's the second part of the question. So, how you represent that mathematically is that you compute the well function for any time t greater than 100 days for the first part by assuming that my pumping well is continues to pump for t greater than 100 days as well, and then I subtract from that the negative drawdown produced by an injection well, which is, when I say drawdown refers to the reduction in water level when a pumping well operates. Negative drawdown means when I inject water into the aquifer, it is supposed to raise the water level. So that's what I meant by negative drawdown, right? So when you algebraically add these two terms together, what you get is the net result of turning the well off after 100 days. Okay, so the answer for the second part would be S equal to Q divided by 4 pi t multiplied by well function U1 minus well function U2. And the reason I have a minus here is because one well is pumping water out, so it produces drawdown. The other well is pumping water in, so what it produces is a raise in the water level, which you can think of as negative drawdown. So that's why there's a minus over there. Okay. Now this U1 is simply R square S by 4 T capital T transmissibility times T small t, and U2 is R square S by 4 times capital T multiplied by T minus 100. Okay. So that's what the second part of the question is, where you want to find out the drawdown after 100 days, an expression to estimate drawdown after 100 days. Okay. So this is all that was expected. And once you have this set up, right, you just have to implement this for those different times that are given. So compute the drawdown for R equal to 20 meters, that is provided to you. Capital S and capital T have already been provided in the question, 500 meters square per day, and 10 power minus 3 is the storage coefficient. So this time T, you have 4 times, 1 and 100, and then 101 and 200. Okay. So for 1 and 100, T is less than or equal to 100 days. So you will simply use the equation S equal to Q by 4 pi T times well function. Almost every single person in the class got this part of the question correct. For T equal to 101 and 200 days, you can no longer use the first equation. You will have to use this equation that I've written down here, well function U1 minus well function U2. When you compute well function U1, you will directly use 101 and 200 as the time. Okay, for well function u2, you will have to use 101 minus 100, so it will again be 1 and 100. Okay, so well function u2 will be the same as the well function that you got for t equal to 1 and t equal to 100 days, right? Which are the first two parts of the computation that you have to do. So which is basically kind of reducing the number of calculations that you have to do, because t minus 100 is basically 1 day for which you've already found the well function, right? So you when you solve t equal to 1 day, you already got the well function for t equal to 1 day. And similarly for 200 days, 200 minus 100 is again 100, for which you already have the well function. So there is, it's actually minimizing the number of computations that you have to do, right? So that's the idea. So the reason for picking these particular days is to if you get the hint, then you can quickly figure that out and then solve that problem, in a relatively easy way. Okay, any questions on this? I'm expecting that there will be some questions on this probably. No questions on this as well.
No, sir.
Okay, anybody who's online, who's joined online, questions from them?
Yes, sir. We are joining online.
Yeah, do you have any questions?
No, sir.
Okay, all right. So oh, and the other thing is, those who directly use t equal to 101 and 200 in the equation and solve for it, there was a when you looked at the numerical answers that you got, that should have given you the idea that something is wrong, because if the well shuts down pumping after 100 days, the drawdown should decrease after, for t equal to 1 and t equal to 100, drawdown should increase. But once the well is shut down, the drawdown should start decreasing, because the well will start recovering, right? So there'll only be residual drawdown. So as soon as you got numbers that are greater than 100 days, that should have given you the hint that something's wrong with the approach that I've used. So and even if you did not know the way to solve it, the method of solving it, of writing this equation, you can definitely use your intuition to say that something's wrong, right? I put in the numbers into the equation that I have, but the number doesn't make sense physically, right? So there's always you have to keep one part of your mind turned on, because even if you use the right equation, you can always make mistakes in the calculations, right? So when the answer turns out and you have an expectation in your head, is this answer going to be greater than something or less than something, or suppose you have a picture of that in your head, when you look at the answer and you know that, hey, this can't be true, it either means I used the wrong equation or I did not use the right equation. I'll say it that way. It either means I did not use the right equation, or I must have done a calculation error, right? These are the only two possibilities. If you can even catch it at that stage, when you write down the answer just by looking at the numerical values, you can see that there must be something wrong. Otherwise, why is the drawdown increasing? It shouldn't, right? So that can be a soft check, which allows you to maybe then comment on it. And then depending on whether you have time to fix your error or not, I mean, considering that it's a timed environment, right? You're doing this under the constraint of time. You can always apply these checks, mental checks, and at least comment on it, saying, I was expecting it to go down, but it didn't happen. So I'm assuming that there's something wrong in my procedure. So that gives me an idea that you've understood it physically. It's just a matter of converting that physical understanding into a mathematical equation, right? There's always going to be a gap between the two. It need not necessarily be, uh, uh, you know, uh, so basically what I'm trying to say is build your intuition, physical intuition, for what you expect the answer to be, right? To get it correctly computationally or numerically is not as important as getting it right with your intuition. Once your intuition is fine, figuring out these equations are a matter of, it's relatively easier. Okay, so okay, so I'll stop with that. We'll move on to the next question. Okay, derive an expression for the hydraulic head in a 1D unconfined aquifer at steady state. with two constant head boundaries at both ends of the aquifer and uniform recharge along the length of the aquifer. Okay, so now what I would um, uh, suggest is that sometimes if you just pay attention to the rest of the question paper, it can help you in another question. For example, so if you go back to the second question, what you were given was an unconfined aquifer situation, and this was for 2D. Now I take the same equation and apply it to a 1D system. So all I need to do is get rid of the second term. Okay, that becomes the starting point for me to, right? So if I get rid of this term, it becomes a 1D equation, and of course it's also steady state, so this term also goes out. So these two terms go out. I'm left with my starting governing equation to solve problem number 4. Okay, so you can write the governing equation for this one-dimensional unconfined aquifer at steady state. So take the equation that was given in problem 2, get rid of term number 2, which is the y term, and term number 4, which is the right hand side, the transient term, and you already have the starting point for solving the problem. Then after that, it's a matter of rearranging the terms, integrating the equation a couple of times, and you have the answer. You will have h square equal to some constant times x square plus some c1 times x plus c2, right? After that, you just apply the steady state, the constant head boundary conditions at x equal to 0 and x equal to L, and that will give you the expression for the hydraulic head in the aquifer, h square equal to some constant times x square plus c1 times x plus c2, and you will find c1 and c2 appropriately using the boundary conditions. Okay, so that was the first part of the question. Second part, using that expression h square equal to whatever equal to so and so, ax square plus bx plus c, using that equation, I wanted you to obtain an expression for the location and height of the groundwater divide. Now, the groundwater divide is the point at which the flow directions in the aquifer go in the opposite directions. That point is referred to as the groundwater divide, which in this case would be the location at which the water table reaches its maximum height, right? Once it reaches its maximum, which means that on either side of that maximum, the water level will be declining. So we know that water always flows in the direction of declining total energy. So if the water level declines on both sides of a particular point, that point being the maxima, that point must represent the groundwater, so-called groundwater divide, which divides the region into two halves or two portions in which the flow directions are opposite to each other. Okay, and we are just asking you to identify what is this location x max and the height h max of the groundwater divide, right? So the way to do that is to set the derivative of your h to 0, right? So you will have an expression of the form h square. Whenever I write 2, it does that. Something wrong with, right? So a x square plus bx, oh my god, plus c. Okay, so you have an expression of this form. If you differentiate this once, really sorry about this. You get 2h dh by dx equal to whatever 2ax plus b, and at the maxima this must be equal to 0. So if you rearrange the equation, you will get x equal to minus b by 2a, and since you know a and b, you can find x max, right? By setting this first derivative of this equation to 0, you're able to figure out x max. and then that becomes the basis for us to uh, 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 find the x max. And then once you have x max, you just substitute that back into equation number, the equation above, and that gives you h max. Okay, that would be the first two parts, uh, finding x max and h max. And then the next part of the question was, at any given location, how will you estimate the flux? Now I'll keep this on the side, and then I'll write over here. The flux is basically Q. Now a lot of people either did not miss that part of the question, or were not aware of how to find the flux. So the flux. Oh, I think I know what I've been doing wrong all this while. Maybe now it'll be better. Okay, so the flux Q okay, there's a washing machine in the background that's making some noise. Okay, so the flux will be minus K H dH by dx. I'm really sorry about this. I've been using this in the past, but somehow it's giving me a lot of trouble. Okay, so Q is minus K H dH by dx. Now the good thing is, this H dH by dx, you already have the expression for that. What is H dH by dx? You have it over here. 2 times H dH by dx is 2ax plus b. So H dH by dx is simply ax plus b by 2. Right? So you can take that. What some people did was to take dH by dx separately, and then multiplied by or divided by multiply that by h, and so on. So it was, so they actually had ended up computing h once, and then you multiplied that with dH by dx, and then put that in here. So they had to do lots of unnecessary computations. It was not wrong, but it was not needed, right? Because you already have h dH by dx here in this expression. So you can just pick this up directly and plug it into Q, and that will, and multiply it by K. That gives you K times h dH by dx is simply ax plus b by 2. So that will save you a lot of computations, unnecessary computations. Unnecessary in the sense of time. It is not necessary to do it that way. You do it the long way, that will give you the right answer, but you can save time by just picking up h dH by dx directly from this equation. Okay. All right. So then that will give you an expression for Q at any location x, right? So what you will get here is an expression in terms of x, right? It will be ax plus b by 2. It's in terms of x, which you can use later on in the next part of the problem. Now, for the specific case of L equal to 1000 meters, K equal to 0.1 meters per day, and R equal to so and so, and constant head values at both left and right boundaries equal to 10 meters above the datum, find x max, h max, and the direction and magnitude of flux. So now, I noticed that a lot of people, even when solving for x max, assume that both left and right boundaries are at the same level. You don't have to do that. I mean, you don't need to do that. It's not wrong, but that's an assumption that's not inherent in the problem. The first part of the question is for a generic case where you need to find x max and h max for any value of h, h naught and h1 and h2, or h naught and hl, whatever you call those values, right? So when you get x max in general terms, you can use it even when the head values in the left and right boundaries are not the same. It can be used, of course, when they are same, because H1 and H2 or H0 and HL simply cancel each other out, right? But when you solve for X max for the general case, you keep it in terms of H0 and HL rather than eliminating those terms. Okay, so that is something that you have to pay attention to. So the second part of the question, for the specific case, you take the general equation and then use whatever is given in this particular example. So this is a specific example. So the general equation, all aspects of it need not be applicable to this general example. Or to put it the other way around, don't take the specific example and substitute that in the general equation. Don't assume H0 equal to HL, or don't assume H1 is equal to H2. It's not. It need not be. Okay. So, and then the other thing that I noticed, some people caught on to it very quickly. Some people put in all the values into the equation and solve for X max for this specific case. You don't have to. If the two boundaries are at the same level and I'm getting recharge, X max will be at the midpoint, L by 2, 1000 meters divided by 2, 500 meters. So there also you can save time by not getting into that computation and do all of that only to find that L is, after all, X max is L by 2. So these are some of the again, as I said, there's nothing wrong in doing all of it and finding out that X is L by 2. But the problem is giving you a specific case where both the boundary conditions are the same, and which automatically indicates that the midpoint will be bang in the middle of the domain, right? So that is where you have to have that connection between the physical process and your the mathematical procedure for calculating X max. That is the procedure for finding X max. If you follow the procedure, you will get the answer. But if you have the intuition, you can just quickly arrive at the answer without having to go through that mathematical procedure, right? So I think there is value in that, right? It's not a mere case of, I have an equation for X max, put in all the values, you will get the answer. Of course, you will get the answer, and everybody got the right answer. I think almost the vast majority of the class who solved this question got X max correct. They got L by 2. There's no problem with that. Okay. But I'm just looking for those hints where, people have not gone through the, gone through the steps to get the answer, but have arrived at the answer just because they know based on their physical intuition. Okay. Anyway, it's good either way. I'm not complaining. I'm just saying work on these things, right? So everything is not about following procedure and arriving at the answer. Sometimes intuition can also help. Of course, we solved that one particular problem where intuition tripped us up, but not every time your intuition may be wrong. Okay, so anyway, and then H max, you just substitute that value of X max, and then you get the value of H max, and then the direction and magnitude of flux. So if you use this equation minus KH dou H by dou X, you will find the fluxes at any given value of X, and the two values are given, 200 meters and 600 meters. Now again here, if you know X max is 500 meters, when X is less than 500 meters, the flow will be from towards the left boundary, and when X is greater than X max, 600 meters, the flow will be towards the right boundary. So now you don't even, to find the direction of the flux, you don't even have to compute anything. You can automatically say for X equal to 200, flux will be towards the left boundary, and for X equal to 600, flux will be towards the right boundary. So this is again a place where your mathematical, sorry, not the mathematical, the physical intuition comes in. Even if mathematically you get, suppose you put in, you don't have the negative sign, you will get a positive or a negative answer, but your intuition should kick in and tell you, oh, you know what, I know that X max is 500, I'm sorry. So 200 flow must be towards the left, and at 600 flow must be towards the right. So there again, your intuition can really help in getting to the answer without having to go through the steps, at least for the direction. Magnitude, of course, you have to go through the steps. There's no other way of arriving at the answer. Okay. So with that, I'll stop for today. We will meet again on Friday as usual, and then we'll see. So happy Dashara to everybody. Tomorrow is, of course, holiday, Vijay Dashmi as well. So, happy Dashara, happy Vijay Dashmi to all of you. And we will meet again on Friday at 11 a.m. Okay. Thank you so much. Take care and see you on Friday. Ah, the camera is on. So I see Tanvi is there and Anvesha is there. Who else is there? Camera, maybe it can turn. I don't know. It's okay. All right. Thank you so much, guys. See you on Friday.
Thank you, sir.